Welcome back. So before the next session starts, last reminder about voting. Vote for the best demo and best poster and best photograph. So 3 tasks if you haven't already done so. So last reminder.
So welcome back. I'm Hajime Nagahara from Osaka University. I'm chairing this session. So I'd like to introduce first, invited speaker, Ivo Ihrke. He is a professor of the computational sensing at the University of Siegen, Germany, and also member of the ZES, which is the center of the sensor system at the university. And also he is affiliated with the Fraunhofer Institute for High Frequency Physics and Radar Technologies. So today his talk is computational imaging across the scales. So please welcome him to the on the stage.
Okay, thank you very much. Actually, before starting this talk, I have to say it's sort of a bit of an unusual invited talk in that it includes a lot of work of other people, because I basically try to draw some connections between different imaging domains and hopefully motivate you to sort of look beyond your own domain in order to discover maybe methods that other people are using, tricks other people are using, and sort of do cross-domain transfer. Yes. So the idea to give this talk basically came from actually one of my most challenging talks recently, which was basically something that's organized by our university, which is called the Children's University. So I had an audience of 8 to 10 years old, which I tried to explain to the scales in the universe. And they can count to up to 100 approximately. Yes, so I don't take you for this audience, but I simply want to make a walk through the scales in some sense. You probably know this movie Powers of 10. It's a bit of an inspiration behind this. Yes, I hope you enjoy it. So the guiding figure through this talk will be this one. Yes, so we will be covering actually imaging in radio waves. So these are distinguished basically by the fact that we can measure phase, and then basically we're moving to the optical domain where we can no longer measure phase. Yes, but I hope to show that there's a guiding principle basically behind understanding all of these. As a motivating example, I would like to use the Event Horizon Telescope, where we also had a keynote by Katie Bowman at this conference some years ago. Yes, and you've probably seen this kind of picture in the news. Yes, maybe not the movie version that is shown here. But anyway, so it's been taken by the so-called Event Horizon Telescope, which is not actually a real telescope, but it is a virtual telescope consisting of a lot of different radio telescope stations that are linked by atomic clocks together and synchronized very precisely. Yes, so these are shown here. And these together build basically a camera that has an aperture the size of Earth. Yes, so it is very big. That's why we can actually image objects that are very far away. So now I was interested in how this works, and this is basically a paper on the subject that I can understand. It's basically a computational imaging one, where we have our usual optimization, min, some quantity, which is basically based on the image, and basically subject to constraints using regularizers, TV, and sparsity in this case, and a data term that includes the amplitudes and the phases that are measured by these telescopes. So how does this work? It's basically very large baseline interferometry. That's what the name is of the technique, the underlying basic sensing technique. It's basically any pair of these radio telescopes will basically sense a signal from a distant object at slightly different times. Yes, and these times, basically, due to atomic clock synchronization, can be measured by correlation, which then gives you by this triangle sort of this propagation direction of the wave. Yes, so any pair of telescope actually can measure one such plane wave of an object in some sense. So this is a diagram they use to denote all the plane wave components that we see over here. So any point in this diagram will basically be one particular angular direction. So it is actually a virtual kind of aperture over here. We can measure an amplitude in the phase, And there's actually additional measurements, like these trajectories here are basically by the rotation of Earth, additionally generated points in the aperture. Yes? So we get a non-uniformly sampled aperture over here. So just to remind and introduce this idea of back projection or time reversal that Sylvain introduced. Basically, if we have a point in the aperture and there's a plane wave, we can basically back propagate it to our image plane, which will be the black hole, obviously. Basically, when we intersect this image plane, we will get a constant if we are orthogonal, or we get a sinusoid when we're basically back projecting at different angles within this plane, which is why we call these Fourier components, and this is actually for a transformation of the image that is just not completely sampled. If we sample it completely, we obviously get our diffraction pattern over here, which is resolving the spot, which is a sync pattern. The intensity of that will be our Airy disk typically. So now the challenge is that the aperture is not fully sampled in this radio astronomy case, and therefore there is a minimization problem that's being solved. I took it from the paper over here. So these F matrices are partial Fourier transforms to generate these individual spots. A is extracting the amplitude, B the phase, and we're minimizing against our measured data. So, and then here we're getting the result. This is basically from the 2017 paper that I read, and the other one is the published result. Yes, so they actually tried a lot of different algorithms in order to validate that they see the same structures, because they were looking at something that is completely unknown to validate that. Okay, so this is essentially imaging of a point object. Yes, is a super resolved imaging of point object. Actually, the size of it is given by something like lambda over 2NA, but they do it in arc seconds. I calculated approximately 1/100th of a light year of a PSF resolution on the previous example. So now if we want to move beyond a single point and image many points, actually at pretty similar wavelengths, so these are millimeter waves over here, we are ending up at radar imaging, yes, so-called synthetic aperture radar, which uses wavelengths between tens of centimeters and millimeters as well. So here it's an image of my university. Actually, we're over here in this kind of building, and this is a so-called SAR image, synthetic aperture radar. Yes. Okay, this principle is relatively simple. Basically, we're having a satellite that is flying across a scene. It's emitting pulses. So this will actually be quite relevant to these non-line of sight people. Yes, it's pretty similar. We're emitting pulses that are hitting basically the ground, and then every point on the ground will be scattering back a spherical wave to the satellite that is measuring this kind of echo. And it will turn out that if we use these echo measurements, we can build up something that is called a synthetic aperture, which is basically the equivalent of a real aperture lens. So let's look at how this works quickly. Assume we are emitting a Dirac pulse. In practice, it will be a little bit different, which is blue over here. Then it's traveling to a scattering point. It's basically at the scattering point, we get a spherical wave which is emitted back, and there is basically the time delay that is associated to this distance r over here that is being recorded over here, or rather we record the complex signal at this time point. So what's important is that the energy loss is quite significant. It's r to the 4 because we have two spherical waves. Yes. So if we do this several times, obviously we get basically measurements at these different times, and we can basically invert this process in this kind of time reversal that Sylvain explained very nicely. Yes, and we can actually superimpose all of these spherical waves in order to reconstruct the scattering point and possibly lose a bit of contrast on these other points over here. Yes, so in practice we do this typically in a plane, which is the image plane, but it could also be done to any kind of ground truth known geometry. For example, in satellite imaging, it will be LiDAR. Typically, it's a much smaller field of view over here, and the circles are not as different as I show here. So there's a lot more complexities, actually, because we have a moving platform, for example, we need to compensate Doppler effects and so on. But that's the imaging principle. So the one thing that I want to mention, though, is that actually we can't make a Dirac pulse, and we would need a lot of power to do so, to make a very short pulse. So people are actually sending out a so-called chirp, which is basically a linear frequency kind of varied modulated signal. And then they apply an optimal filter, which is called the matched filter, which is actually the autocorrelation of the chirp, which it does something called a pulse compression. Yes, the output of it will be a sync, where the distance over here will depend on the bandwidth that is included in the frequencies of the signal. So we're basically back to a bit fuzzy lines intersecting here, and not exactly these ones. So I also wanted to mention a relation between back projection and back propagation in networks. Yes, it's actually the back projection operation is basically a back propagation on a quadratic linear term, so inside linear quadratic norm, used with an initial guess of 0. So it is a very crude kind of reconstruction, you could say. Yes, it's not an inverse matrix, but basically this conjugate matrix that was mentioned previously. And then we can see, just as Sylvain explained, these kind of measurements as a virtual aperture, as a virtual kind of lens that we synthetically, by phase shifting and summation, basically can generate images with. So in my group, we actually have a portable, custom-made SAR system. It's called the Hitchhiker because it's supposed to be hitching hikes somewhere on planes and so on. Yes, so that's the sender unit, receiver unit over here. And I want to show one particular result that I like from my colleagues at Fraunhofer Institute. And this one is now basically such a SAR imaging where a light airplane is flying around this roundabout in a circular motion. Yes, but what's sort of interesting about this is that they do not synthesize an image from the whole circular aperture, but they are using sub-apertures. And because there's a motion, they can actually generate these kind of SAR videos. Yes, so it's actually time-resolved SAR imaging over here. And we can note a couple of effects over here. Like, for example, we have a parallax motion on this building, which is a gas station. Yes, so this is encoding the height. You can actually do photogrammetry with this. The second part is basically these very bright kind of structures over here. They are called layover. They are caused by these big billboards over here. Yes, because an echo actually that hits the top arrives earlier than one that is at the bottom, and so it's projected to the ground basically in the direction of the airplane. And the third, so we can correct basically these two effects, and then there's one effect that I want to show that where we have no solution. So if you have some idea, it's probably welcome. You can see these shadows over here. These are actually cars moving around, but the cars themselves are not visible. Why is this? It's basically because we have moving objects. So there's another Doppler effect going on here, which is basically creating these kind of flying ghosts that are passing around here. Yes, and it's very difficult to separate these or compensate for these. So any kind of ideas on how to deal with this, I think, would be highly welcome. Okay, so for the registration, actually, we found a very simple kind of transfer knowledge. We just applied optical flow and introduced it to this community. They are just using correlation, for example. So a classical TV L1 performs reasonably well, much better than correlation over here. Unfortunately, machine learning doesn't work out of the box. Basically, the data is too out of domain, and we have very little data for training. So that's a challenge for retraining it over here. Another aspect is this layover. Here, people are doing something called SAR tomography. Yes, so this is basically trying to resolve the third dimension. So essentially, you could back project to all these different planes at once, but then you get a very smeared kind of image. So what people do is they introduce a sparsity assumption and say that there's only like 2 scatterers in one column, so to say, or 3 maybe. So they add a sparsity prior and solve the real inverse problem instead of just doing the back projection. So here's a layover from another group onto a satellite image that shows basically how these 3-dimensional structures are being reconstructed this way. Another thing that I found is interesting is passive bistatic SAR. So these are actually two things here, bistatic and passive. I will first explain bistatic. So normally people say, or basically this co-located sender and receiver, they call a monostatic configuration in this community. Yes, and if the receiver and transmitter are in different locations, it's called bistatic. Yes, so then we get these kind of paths over here for measuring these different points for back projection. And basically something that's emerging right now and is pretty hip is basically these passive SAR, which is basically using not active senders, but is reusing other kind of electromagnetic radiation, like from telecommunication satellites, satellite fleets like Starlink, telecommunication towers. Actually, in the wider radar community, people are exploiting wireless routers because like 5G is having frequencies pretty high up. So actually people will be able to track your motion in your house and things like that. So I think that's sort of something to be aware of. Okay, so if we move a little bit higher up in range over here, we basically get to terahertz imaging. So these are basically in between the optical and the electronic worlds, so to say. Yes, it's basically a frequency range that has been quite hard to reach. Yes, so in optics we have time-varying electrical fields. In electronics we have current densities. Yes, and we're sort of, they can basically move from both sides into this domain. So we have a group in Siegen working on this topic, and we're working together with them in a program called Learning to Sense, which is basically trying to use machine learning for improving the sensing matrices over here. So it's basically this kind of, I mean, most famous probably for these airport security scanners that can look beneath for concealed objects in persons. So this is an example with an electronic key that has a transponder inside, so you can look inside because the waves have a certain wavelength that sort of penetrates these materials. So now in this domain, basically the devices are relatively immature still. And so all the groups basically develop sensors, sources, and the application scenarios simultaneously. So basically the algorithms are not super top-notch yet, I'd say. Yes, so I think there's a lot of potential for transfer here, especially from the non-line of sight community. So that's how such a setup looks like. They can actually use lenses now to already focus these radio waves. Here is basically a scanning type of system that they have in their lab. So you have a point kind of source over here imaging through this object, and there is a detector on the other side, and they're sort of co-moving. Yes, but the group is pretty much interested in making this faster and cheaper. So essentially the kind of detector that you have in here is the same one that you have in these radio telescopes. So they're pretty expensive. Yes, so you don't want to make an array out of them. But they want to make an array in order to do the whole thing faster. Yes, they don't want to do the scanning all the time. So they actually developed sort of silicon kind of detectors, little kind of antennas that are put behind silicon lenses that can basically make the antenna shape over here, yes, which is basically beam-forming apparatus. And they create a full 2D aperture in this way, having a one-dimensional aperture with these detectors, and the other one-dimensional aperture by mechanical scanning over here. But then it's actually pretty much the same as the SAR imaging that I explained, yes, except that now we have higher frequencies, so it's pretty hard to make these analog chirps to be pretty linear, like in frequency. So what they do instead is a nice trick, I think. They use continuous wave sources, but then they actually, so that means they can only measure an amplitude and a phase, but not like the actual time-resolved profile. But then they do a temporal frequency scan in order to perform also synthetic pulse synthesis on top of synthetic aperture. Yes, so the picture is basically this. So they use different frequencies. Yes, these are, oh, actually this is supposed to be the transmitter. Yes, I know I'm back projecting from the receiver on the slide, sorry. And now we're superimposing basically these different frequency waves over here. If we add them coherently, basically you will get a pulse yes, which is basically a Fourier synthesis of the pulse. Again, we have the bandwidth sort of limiting the size of this pulse. Yes, so you can actually do back projection of all of these different quantities that you have done in the Fourier scan and basically obtain something like this. This is a validation over here. This was a simulation of the setup, and this is an actual experimental PSF that the group achieved. Here's a test target and the depth recovery of this kind of object. So with this, I would like to move to the optical domain. We had a poster on Fourier pyrography. I just want to quickly introduce the concept because I think many of you are familiar with this. So basically, we're having, instead of a uniform, a single light source in a standard microscope, we are having basically a set of LEDs and illuminate the object from different directions. Yes, and we add we add a phase retrieval algorithm in order to basically reconstruct complex images in order to be able to coherently superimpose those. So how this is working is basically shown here in the sketch. So we illuminate from these different directions. And also Sylvain had like this nice animation of like a slightly moving source and how basically the scattering profile moves with it. It basically tilts in the same direction. Yes? So in the angular spectrum, because all of these are Fourier components, you can see this basically as the object spectrum being shifted, whereas we have the lens basically that is doing a bandpass filter on these things. So they should overlap in order to enable the phase retrieval over here, because we only measure the intensities over here. A nice connection is also if you change this into an alternative view now, I just tilted all of these, you can also see this basically as sort of a form of multi-perspective imaging on a scattering sample from different directions. Yes, so it's actually quite equivalent. So the cool thing about it is that it surpasses the resolution limit, lambda over 2NA of the objective, while maintaining the field of view. Yes? So you increase the space bandwidth product without mechanical scanning. So I just wanted to show you how this image looks like. So that's one taken in our microscope. It's not a super resolution one yet, but here's the actual data. So the center, so these are the different LEDs over here. Yes, and I want to convince you that there's data in this black region over here. Yes, so if we move around here, you see that actually now we're moving in the black region, and how the contrast is good enough that you can see that there's actually edge structures over here, which are basically the scattered so-called dark field components that contain the high frequency information over here. Yes, and you combine those essentially to compute the super resolution image. Actually, what I wanted to point out as well is here's a little kind of picture on the left that basically shows these UV illumination components under the mouse cursor. So it pretty much looks like a lens-led microscope, but it's not. It's actually a diffraction pattern that has been convolved with the aperture of the lens, the imaging lens, the objective. So this I want to convince you of by basically explaining the last technique here. It's electron microscopy. So how did I get to electron microscopy? It's basically, I was working in a company, so I'm working a bit on electron microscopy. And then I got invited like maybe a year ago to a computational microscopy workshop at IPAM for 3 months. So I went there and I was excited. And suddenly I found myself that it was a computational electron microscopy workshop. Yes? And I didn't know at all what to do with this. So there was 50 material scientists in me. And it was a bit hard for me initially to get to know what they are doing. Yes? So I know this, right? So we start, I mean, so far we've been talking about Maxwell's equations, basically, and actually the time-independent wave equation, so scalar wave equation. So polarizations, some people use it, but yeah, usually the main ideas can be understood with this one. So now it turns out like that electrons, they're much more subtle objects, yes, because they have a mass and a charge, and so they're influenced by all kinds of things, and it's quite terrible. But there is an equivalent equation to Maxwell's, which is called Dirac, equation, and then there's a couple of similar approximations. Basically, this low speeds approximation here, I mean, photons have constant speed, so it's not there. But apart from that, basically you go the same steps to arrive at the so-called time-independent Schrödinger equation, which is also a scalar wave equation. And you can understand actually electron microscopy also in terms of scalar waves, which I found relatively interesting. So then people are doing so-called pyrtography, which is the dual of Fourier pyrtography. Yes, so if we go from our Fourier pyrtography setup, just imagine that we sort of invert a pixel. So this was a pixel, but now we consider it to be a LED, so Helmholtz reciprocity. Yes, and we're sort of focusing on a spot on the sample over here and measuring these different diffraction components. So we had LEDs here before, so now they are considered to be photodetectors. Yes, so in this case, you can also see that we're actually measuring different parts of the Fourier spectrum over here. And again, it's going to be intensity and not phase. So you will need to do phase retrieval on top of it. So that's the picture that you see here. Yes, our electron beam is then incident on a specimen over here. And these days, people have actually access to two-dimensional direct electron detectors making images. And these images will be recording these kind of diffraction patterns. And they are actually the same kind of patterns that we're having, that I showed you in this Fourier pyrtography data set. And the good thing about it is that these people actually know what to call this data. Yes, and it is particular the Wigner distribution function. It's a physical realization of it. So I was always struggling with getting behind the math. What is this Wigner distribution function? Yes, but it's actually this kind of diffraction pattern that I showed you over here. Yes, and it's just simply switched image plane and aperture plane. Obviously, there's different resolutions and different geometric kind of considerations at play over here. So a link between light fields, I didn't mention them so far. Yes, and the Wigner distribution function is basically was given early in some ICCP papers by Mark Levoy's group. If you're interested, this explains why there is basically a convolution between the spectrum and the aperture of the imaging system over here. What's important is that this is actually, you can see this as a localized angular power spectrum, yes, which then enables or it actually encodes the relative phase of the signal. And what people do in this domain, which I find super cool, is that they actually do this in a rotating fashion. So they not only do pyrtography, but they also rotate the example. Yes, so that means that you can actually reconstruct an exit wave phase for each of these directions, and afterwards perform phase tomography in order to reconstruct a three-dimensional version of these unordered materials. Yes, so you can individualize individual atoms, and these are basically phase profiles of the atomic potentials. That also works with a bit more classical detectors, like this high-angle annular dark field detector over here that's integrating over a circle instead of 2D resolving the diffraction patterns. These are individual atomic species, and material scientists can actually compute forces between atoms and all these kind of things from this kind of data, which is, I think, super interesting. So with this, I would like to finish my walk through the scales of actually not computational imaging, maybe synthetic aperture imaging. Yes, we basically had objects that were like fractions of light years large and picometers large, hundreds of picometers, yes, individual atoms. Yes, I hope if there was one or two things that you could sort of relate to and connect with your own research, then I have achieved my goal with this talk, and I'd like to thank you for your attention.
We have time for one or two questions. Any questions?
Very cool talk. Can you explain a little bit the Doppler car artifacts in the SAR imagery? Sort of.
This
hadn't
video,
seen this before.
this video that I showed, yes.
Yeah.
I mean, basically, it's like, I mean, a moving object will basically stretch and introduce the Doppler effect, right? So now this basically changes the composition of your pulse, the frequency composition of your pulse, and in this way, basically moves because you're back projecting it onto this plane. It basically is moving these kind of components to different places, yes? And since the object motion is not known, it's basically ending up in sort of unpredictable places. I mean, we can basically compensate the Doppler from the moving satellite, for example. It's more difficult for an airplane. There you need very accurate GPS in order to do that. But for these kind of cars and so on, basically, we don't know how to do it. Yeah.
Okay, no, thanks for speak up. Yeah.
Thanks for the very nice talk. So I had a question. So you only cover mostly electromagnetic waves. Are you looking also at acoustic waves? I mean, I'm thinking specifically of seismic wave or echography, where there are many also similarities.
Of course, there's 25 minutes for this talk, but actually people are doing this obviously also with acoustic waves for non-destructive testing, for example. Yes, they also do this back projection kind of thing. Actually, you can do it actually to predict also like some sort of pressure fields. We're working a bit on microfluidics at the moment to manipulate particles for the microscope. Yes, and there the acoustic fields basically behave exactly in the same way, obviously. Yeah.
Okay, so let's, thanks speaker again.
So I give this one.
So we are going to move on to the session, last session of the ICCP accepting paper. The first, presentation in multi-color path tracing and the statistical event detection for event camera. The speaker is Manabe. So you can start.
So thank you for the introduction. Hello, my name is Yuichiro Manabe. I came from Chiba University in Japan. Now I will be presenting about our paper, Monte Carlo path tracing and statistical event detection for event camera simulation. First, let me explain the event camera, but if you listen to the first day's keynote of Professor Scaramuzza, you already know about it. The event camera is a special type of camera which detects only brightness gap asynchronously. So look at these two videos. The left shows the bus taken by RGB camera, and the right shows the same bus taken by event camera. In the right video, you can see that only the temporal gap is captured compared to the left. And event cameras have several advantages over RGB cameras. For example, in the video on the left, the lower part of the bus is blacked out and not visible. But in the right video, the front tires are clearly visible. As you can see, event cameras have a high dynamic range. Also, the background area in the left video is not shown in the right video because there is no moving object and thus no temporal brightness gap. So the amount of data from event camera is smaller than RGB camera. For this event camera, if there is physically based event camera simulator, it can accelerate the research and development iterations. Since event cameras are primarily targets real-world environments, physically based methods are effective because they can reproduce realistic lighting conditions. However, there's a problem when applying physically based rendering method to simulate event cameras. The reason is that current image-based event camera simulators do not assume Monte Carlo path tracing, which is a common technique of physically based rendering. Therefore, as shown in the left box, with the current image-based simulators, the process involves rendering a 3D scene as an RGB video or RGB frame and then detecting events from the given RGB video or frame. However, what we want to achieve is, as shown on the right, to perform Monte Carlo path tracing on the 3D scene and directly obtain the events. So there are some problems in current simulators. First, current image-based event camera simulator is based on a black box renderer. And when we use Monte Carlo path tracing as a black box renderer, it typically samples paths uniformly over the image plane. However, this is time-consuming considering the data sparsity of event camera. Therefore, our approach statistically estimates the temporal brightness gap from a few path samples, then detecting events by sampling paths of pixels where gap seems not to be small. Specifically, in our rendering pipeline illustrated on the bottom, we uniformly sample a few paths from a 3D animated scene and use a result to estimate the brightness gap statistically. The middle video shows the estimated gaps. In this scene, for example, the ceiling or the back wall have a small gap, but the floor and window frame have a large gap. So we continue to sample only the pixels with a significant gap, like in the video, yellowish pixels, and discarding sampling for pixels with small gap, like purplish pixels. This way, we can even render event in the shorter time. So first, let me explain how to statistically estimate the gap from a few samples. In Monte Carlo path tracing, multiple samples are collected for each pixel. So we can calculate their sample mean and sample variance. And now, based on the central limit theorem, we can approximate the distribution of the sample mean as a normal distribution. The figure on the left shows us an example of this distribution. So now, if you look at the same pixel at two different time points, let's call them A and B, so we can get the sample mean distribution for both. And using this, we can get the distribution of the gap between them. This is thanks to a reproductive property of normal distributions. So you can see the gap distribution in this figure on the right. However, statistical modeling of the gap is not so simple. In previous research, Hu et al. Showed in B2E that the event camera performs a logarithmic light transformation on the luminances before comparing them. It is called the lin-log transformation. However, the sample obtained by ordinary path tracing is luminous. Therefore, simply finding a sample statistic will distort the distribution of the sample mean. This does not allow for correct statistical event judgment. So we modify the path tracing method and directly sample the lin-log transform luminances for correct statistics. So using this approach, we are able to obtain the lin-log transformed gap distribution per pixel. Next, I will explain how we statistically determine when an event is unlikely to occur. So event cameras do not detect all gaps as events, you know. It outputs a gap as an event only when the gap exceeds a threshold tau, which is specified in advance by the user. So event detection can be rephrased as a problem, like whether the gap exceeds tau. This problem can be treated as hypothesis testing on the gap distribution. For example, let's assume we have a gap distribution as shown on the left in the figure. In this graph, the red dashed line indicates the mean of the gap, and the black dashed line indicates the threshold tau. From this, we use a statistical method called student t-test to determine whether an event occurs or not. The test statistic t is calculated as follows. So now, let's see how we use this test statistic t to determine if an event occurs. Take a look at this graph showing the t distribution. So if t falls within the blue region, the null hypothesis, events may occur is accepted. And if t falls within the red region, the alternative hypothesis, an event could not occur is accepted, and the null hypothesis is rejected. For instance, if t was such a value like -2.5, indicating that the null hypothesis is rejected, so there is no need to sample paths of the pixel anymore because there is no need to estimate accurate gap. So we discard sampling paths at this pixel. Otherwise, like if t was such a value like 0.5, we sample more additional paths because it is necessary to estimate the gap more accurately. This is our statistical event detection method. And this is the experimentation result of our method. Our method is implemented on physically based renderer PBRTV4. And the baseline method and at the RGB preview is the result of rendering at 4096 SPP, means the sample path sample num of each pixels. And the baseline method and RGB preview was sampled for all pixels uniformly. This is the RGB preview of this scene. And this is a result of baseline method and our method. Results show that our method renders comparable results to the baseline method about 6.4 times faster. And from the sample distribution map on the right, the average SPP for our method was too small. Actually, it was about 700 SPP. In addition, quantitative evaluation was performed by RMSE, PSNR, chamfer distance, and difference score. Chamfer distance is calculated as treating events as the spatial temporal point set, and difference score was calculated with event detection as a binary problem. The detailed definition of them are described in our paper, so please refer to it. All evaluation metrics indicate that our method is not significantly different from the baseline method. We experimented with another scene. This scene is a simple fluid simulation, like pouring water into a cup, and created in Blender. This is the RGB preview of this scene. And this is the baseline and our method result. In this scene, the improvement in execution time is greater than in the previous scene. As shown in the sample distribution map on the right, this is because there are fewer pixels where events might occur in the scene. Therefore, this method effectively leverages the sparsity of event camera's data. So finally, we described the ablation study of our method. First, the hypotheses were tested with two-tailed. In other words, we rejected the null hypothesis 2 when the event should be occurred. This is result, and the two-tailed result is on the right. In this scene, when large gap, in this case, when large gap has detected by chance, we stop sampling the path. This is known as type-1 error in statistics. Then, the estimated ln log luminance for subsequent events becomes inaccurate, so the result was much noisier. And we also tested where we simply compared gaps in sample means without taking the distribution into account. This is result. And in some cases, sampling is stopped when the gap appears smaller by chance. This can result in missing events. So you can see it in the two boxes highlighted in this video. Therefore, it is necessary to consider distribution. And this is a conclusion of this presentation. We propose a new efficient physically based event camera simulator. The key contribution of our method is for Monte Carlo path tracing and statistical modeling of event detection and the significant speed up in event camera simulation using it. The code for our method is available on GitHub. Thank you for your attention.
Actually, in this video, exactly, why is the neck of the bottle disappearing?
Oh,
on the table, like.
In this case, like the. Yes, in the RGB preview on the yes, as you can see in the RGB preview, the top of the bottle is as almost the same brightness or color of the back wall. So in the bottle top of the bottle was covered by the back wall from camera. So it is disappeared by because it did not cause no brightness gap change. So in this scene, the top of bottle is disappeared in events.
Another question from me. Nice work. Can you also model the noise parameters of event cameras with the sampling? Like, for example, can you change contrast-dependent noise, for example?
Oh, yes. Actually, the more detailed the parameter we used for this experimentation is in our paper, so please refer to it. But in this case, like living room scene, the used contrast threshold is about 3.0%. And this scene, the pouring water, the cup of water, like the scene, is rendered by the contrast threshold like 0.6. Yes.
Another question here. So you approximated the luminance distribution as a Gaussian distribution, but is there any empirical evidence on it? I mean, there is one recent SIGGRAPH paper that has proved that for a low sample count, it follows a gamma distribution. So they claim that it goes to Gaussian distribution is SPP is large, but I wonder if you do have any empirical evidence that you can approximate it to the Gaussian distribution under your experimental setting?
Actually, the distribution of the luminances is not that target. I did not approximate that luminance itself distribution. We approximated the sample mean of luminances distribution. So the sample mean distribution is almost it is to be in normal distribution based on the central limit theorem. So we are based on it. But the central limit theorem can apply to any distribution or any probability distribution. So we use it to these luminances. Thank you.
So, high-performance real-world optical computing trained by in situ gradient-based model-free optimization.
Yeah, sorry for the long title. So yeah, I will present model-free optimization for in-situ training the optical computing system. And I'm Guangyuan Zhao from CUHK, and my collaborator are Xu and Professor Renjie from CUHK. And so first, let me emphasize on the concept of the model-free computing optics. So what it is. For most people of sitting in this room, we mostly use the model-based optimization. Means that when we want to optimize some optical system, like a lens or something, we usually derive some physics-based model of the system, and we can do the optimization strategy such as the backpropagation through the physics-based simulator to optimize the parameter of the interest for the system of interest. While the model-free optimization strategies would is relatively not well known, and we will say that it optimizes the optical systems without requiring explicit modeling of height of the system. Yeah, that's what we want to say about model-free optimization. And there are also several strategies for the model-free optimization, and also presented in our work, we have the backpropagation. We specifically use backpropagation through the measure, not backpropagation through the physics-based simulator, not backpropagation through the path. We backpropagate through the distribution to optimize the system. Yeah, and for this talk, we specifically focus on the task of optical computing. What Professor Siavash has also introduced a bit. The optical computing, long story short, it uses light waves for the high speed and low energy data processing, and they have some in recent years, it has been investigated for several decades, and recently there are also the cool demonstration for the edge detection, sensor recognition, and some simple motion detection, but all are simple tasks. And so the problem we want to tackle in our work is about the reality gap. We find that in the training of the optical computing, reality gap exists. So issue of reality gap, I mean, it has been emphasized a lot in the robotics community, right? When they want to optimize some robots, in the computer, if we want to transfer the robot in, optimize the parameter into the real-world robot, there is a reality gap. But I want to say that it also was attention here for this room for the ICCP, and we also needed to pay attention to this. And here is some example that. We have a simulator-based training. Usually we train some our system in a simulator, with the model F-hat system, and if we transfer the optimizer parameter or some system parameter to the real system, we say that I would say that there would be a reality gap between the simulator and the real-world system, and that's what we want. That's the problem we want to solve in our work. And so here is a tool analyzed on a sandbox, our a tool simulator. We have like a single layer of a computer system. So here we have input layer, we input object, or I have some like this object computing layer with some weight, and this is output layer. It's just a simple one layer of the computer system. If we impose very like slight shift, we say like the slight shift like the angle, like the very tiny angles of rotation, or like the shift of the micrometers. We see that if you don't have like any like electrical like the post processing, the accuracy will degrade very quickly, like very like dramatically with like slightly missed element. Yes, so that's one example of the reality gap, like the. So like how to mitigate the reality gap. So a simple solution is to do the institute training. Like the long story short, institute training like meaning training like the system in the training like some system of interest with the real world system, and it will incorporate the system like the missed element or mismatches in the forward process. But how to do the backward update? So there is a very good work like published in like the 2022. The two works simultaneously, all about a similar story. They have like the we call it a hybrid training. They like in the forward process, they execute do the forward in the real system, but in the backward process, it backpropagates through the the model of the simulator. So it's called hybrid training. But we find that it still involves like the biased simulator, because you can never get the model to be perfect, and also the computation of the simulator is also like intensive, like especially if you want to have a multi-layer diffracting neural network, it will have like a very strong memory consumption. So for our solutions, we only rely on the forward, and ours is unbiased, and we don't have like any simulator involved in the backward process. Okay, and here is like the simple like the comparisons of like the several strategies. The first is a pure simulator-based training. The other is the hybrid training I just mentioned, and the last is ours for like model-free optimization. And we see that we can do the institute training, and the computation is relatively low, and ours is model-free, and we don't have bias. And we have a total task shown here, like with only 100 minutes samples. We see that ours can do nearly do the overfitting, but like if you have like HBT or hybrid training or simulator-based training, they cannot overfit because of the implicit bias in their modeling process. And so how to detailly get the gradient of our estimation. So here is the meat. I will go to the detail about how to derive the the gradient for our update. It has a term called score gradient estimation, and we have a probabilistic object function. And here is some the notations. We have is a classification data set task. And we have input x and output something y related to the label or something, and object computing weight w. And we have a real system denoted by f system with the weight y, and maps the input to output. And so this is a short video, like the derivation of the score gradient estimation. We have a cost function, and here is the cost function for the classification task with the real world system. And in the score gradient estimation, we model W as a random variable and follow the distribution. And in this case, it will be a probabilistic object function, and it will be an expectation of the whole process, and it will be it can do by integrate over all the samples of W condition on theta. And then we take the gradient of the J object function with regard to the distribution parameter theta we optimize. And then we get the following, we do the change of variable, and then we apply the log derivative trick. We can have the following, expression. Then we do the change of variable. We see that in this case we have a some familiar things about like Monte Carlo integration and then we can do the Monte Carlo integration by sampling multiple WJ from the distribution parameter theta, and then we can get the equation as follows. Actually, this equation, if you inside this bracket, if we get it as a reward also we know in the reinforcement learning, if we have a reward here, and we have the distribution here, so this equation is very similar similar to the score gradient estimation used in the reinforced algorithm, and we correspond every element to the single layer system here. We input X as some kind of like the imaging we want to classify into the first SLM, and in the second SLM we have some optical computing weights. So it's a sample. We can feed multiple weights, W12J sampled from the distribution, and we execute this sampled X mask in the real system, and we can get multiple images or return signals, and then with this we can get a reward in this bracket, and we can do the backward update of the parameter. So that's the derivation of the score gradient estimation. And next I show you some results. So this is the result for the simple single layer optical computer system. We have the input layer here and our computing layer here. Input layer will be the digits. Optical computer layer will be the phase weights we uploaded. And here's the example output. So if you use naively, you can choose the regions with the highest intensity to denote if it's classified. And here is the confusion matrix for the minutes dataset, because the minutes are relatively simple here. And here are some results for the single layer system. We show the classification result. So the ideal, for the minutes and F minutes dataset, if for the ideal means that we do it denotes nearly the upper bound of our that we can get for the accuracy, because it assumes no miselement, it's just trained in a computer, and it's relatively high. And for the other simulator-based training, the hybrid training or ours, we see that for our method we can mitigate the reality gap more closely. It can be denoted by the blue color. It will be the method of interest, like the hours accuracy minus the accuracy of the ideal. We see that for hours it can have less relative gap as compared to the other two methods in terms of the training, validation, or testing. And so here is a single layer of the computer system, right? And you can also do it with a two-layer of computer system. That means we have two program layers. We have more layers of computing. We see the result can be continuously improved, and we can get a more closer result. And still, for our model-free optimizing method, we can make it just from 90 to 86. I mean, the result is even more close with more layers, and with given our method. So we, as a side application, we also demonstrated this on the macro-free cell classification. Means that we can classify some WBC cells from their phase responses, and we can classify 4 types of WBC cells. And that's the result here. And so our method do have advantage, limitations. Advantages that ours is more computation efficient, in terms of GPU sources. We consume less GPUs than the simulator-based training or anything involve simulator. But ours lacks we don't for our current implementation, we cannot scale to higher dimension of degree of divisions. And we should note that ours also belong to the zeroth order organization for the graphics and optics. And research was sparse, but in recent years we have seen some advances. So one is we have been asked many times how is our method compared to finite difference method, which is also very well known, and auto-tuning structural light, published in CUHK2024, and it is a good method, but it's the previous implementation does not have very good sample efficiency. And in this year's graph, CUHK2024, we also see the is a method called real grids. It's also similar to our method, but it uses some like the learned local neural proxy from samples to help the organization. And in their paper, we report 35K optimizable parameters. Our method it belongs to the likelihood ratio method, or it is the reinforced method. It can in our like the papers we have like the get a result about 60K parameters, and maybe it can be improved further for either of these three methods. And the takeaway is that we have introduced a score gradient-based model-free computing optics, and we demonstrate super performance in the some optical computing system. And there are like future improvements in the system, such as we introduce nonlinearity, and we can attend to other tasks such as lens design or CGH, or maybe we can progress. Maybe in the future combine the model-free method and a model-based method. Okay, thanks for the attention. And this is our team, and we thanks for the funding support from some Hong Kong institutions. Yeah, thank you.
Thanks for the nice talk. So I had a question about the simulation you showed of the misalignment effect on the performances, right?
Yes.
So it starts with a plateau and then it drops.
Yes.
You know, do you understand the physics behind it?
It's just I think it's yeah, it's
Yeah,
that's why
exactly.
I mean yes. From my naive understanding, it's just because like the region like have shifted a bit. Yeah, so it will I mean light will project to the wrong region because we don't have any post-processing. So yeah, from my understanding, the physics it's just like we have like we would put some PMT or SPAD in some regions, but the regions has been shifted to what we expect. Yeah, that will check accuracy.
Okay, let's send the speaker again.
Sure.
So this sample of this session, Deepmarking, leveraging advanced area of for membership interface
No problem. Hello, my name is Malthe Jelstrup, and I'd like to present to you the joint work of me and Associate Professor Siavash, Arjomand, Bigdeli. The title of our work is Deepmarking, Leveraging Adversarial Noise for Membership Inference Attacks. So first, let me unpack what membership inference attack is. It's the process of identifying if my data was used to train your AI model. So what would I want to use this for? It could be used for data privacy protection or copyright protection. And I would like to illustrate it with a hypothetical example. So let's say that we are a medical institution of some sort, and we have patient data, let's say it's MRI scans. And we want to share them for research purposes. But we're not interested in unauthorized parties using this to train neural networks on. So we might want to investigate other parties and in their models to see if they have used our data without our knowledge or acceptance. However, current MA attacks or membership inference attacks have some limitations. They require white box model access, which means access to internal parameters and training processes and so on. They also require deep knowledge about the model architecture and access to a dataset that is guaranteed to be a non-member. This last part is quite challenging because we are attempting to infer the membership, and now we need access to a dataset that is within the same domain, but we know they've never trained on it. So what are some realistic assumptions that we would like to create a membership attack that works underneath? We want to work under limited black box query access. So we can submit an image to a neural network and we can get a result, and that's it. No more access. We also assume no knowledge about the adversary's model, the architecture or training scheme or anything. And we assume that we have access to our data before anybody else. So nobody can access our data without us first giving them the right. Yeah. And lastly, we assume that our data may be used to train an adversary's model for classification purposes. Any other adversary neural network then classification is outside the scope. So to come up with a way to do this, we ask ourselves 3 questions. What can we measure? And we can only measure the classification accuracy of an adversary's model. We can give them an image and we can see if they are correct or not. We also only assume that we get the actual class that they predict and no confidence scores. What can we influence in this process? We can only influence their model through our own data, which they may or may not train on. And lastly, the only thing we can actually control is our own data. So therefore, we came up with the idea of manipulating the adversary's model with non-standard training data. Essentially, we have some data. We do something to it to shift it. And then we make that data available to another party. And if anybody else, a third party, gets access to it without our consent, they will have access to this new Deepmark data rather than our private data. We can then use the classification accuracy differences between these 2 datasets to identify whether they in fact did train their model on the Deepmark data. So in order to make this Deepmark data, we use adversarial noise. It is essentially, you have a neural network that can classify images, for example. Here, an image of a bird. Then you add some noise to this image. This is learned noise. And you can trick the model into thinking that this is a car or something else. This is what we call malicious noise. But this particular case is a special case. We don't necessarily care what other class the model thinks it is. We just want it to not think it's a bird. This is a very common type of noise in literature. However, there's another direction we can change the image. We can make it look more like a bird. We can make it be easier for a model to identify that this is a bird. So we employ both these types of adversarial noise in our deepmarking process. We train 2 classifiers on our initial private data. One classifier is always frozen and the other is retrained later on. Then we generate this malicious noise and benign noise, we combine it, and we add it to the data. Now we have the first iteration of deepmarked images. Then we retrain one of the classifiers on this data. And again, we generate malicious noise, or we generate benign noise, and then we have this total variational loss that we also include in this generation process to generate the new iteration of demarked images. We do this iteratively a number of times until we converge to some demarked images. So here we see on the left some private images. These are non-noisy. And on the right we see demarked images. As we can see, there is no visual difference between these 2. And on the top here we see the scenario in which an adversary has not trained on our data, so they've only used their own data. And in the bottom, the opposite is true. They've trained on our data as well as their own data. And the yellow bar we see here is the classification accuracy for those models across their independent data. The red bar here represents the classification accuracy on our private data that we know for sure that they don't have access to. Lastly, the deepmarked data. So here we see that in the scenario in which the adversary does not have access to our data, the deepmarked data, they perform worse on the deepmarked data than the private data. This is due to the malicious noise we added. In the other case, where they have somehow gotten access to our data and trained a neural network classifier on our data, they outperform on the demarked data compared to the private data by a significant margin. This means that we can identify, by just seeing the classification accuracy across these 2 datasets, whether they had access to our data and used it for training. It's important to note that in the real world scenario, you would only see the classification accuracy and on the private and Deepmark data, so the red and the blue bar, and through that you would have to deduce whether there was a data leakage of some sort. So what we would like to understand further is how does this correspond to the proportion of demarked images in the adversary's training set. The previous experiment assumed that if the adversary trained on our data, 50% of their data set would be ours. That is quite unrealistic, so let's reduce it a bit. We vary the proportion of demarked data from 50 down to 10%. And on the left here we see the delta between private and demarked data, classification on those data sets, when the adversary has not trained on our data. And on the right, when they indeed have trained on our data. And we see that there's a difference that we can detect down to 30, possibly 20% of the data set. However, we have here set the lambda parameter which controls this total variational loss and how much that impacts our demarking process at 10,000. But if we reduce it by a factor of 10, as expected, we start seeing visual artifacts. But we also see that now the delta between these two data sets is identifiable all the way down to 5% of the data set, maybe even slightly lower. So some instances, it would be fine to have visual artifacts in your data set. Maybe the intended purpose is not for somebody to train a neural network on it. Maybe it's for some other purpose, and therefore noise is not an issue. Or maybe you are more concerned about somebody training that data than the actual use case, and you'd still prefer to increase the detectability rather than having visually pleasing images. If we compare ourselves with the current state of the art, it's important to note that they only have normal data. So we give up a huge advantage in the deep mining process. We don't have access to a twin dataset that we can compare against. So this, we see that across all their experiments, we improve the performance by a couple of percentage points, but that is only due to the addition of deep mark noise on the images, nothing else. So even in the most simplest case, we still improve performance. Thank you very much for your attention, and if you have any questions, I'll try to answer them.
Hi, I kind of have two questions, if that's okay. So my first question is, I may be misunderstanding your process, so please correct me if I'm wrong. But it seems like you come up with the malicious noise through training your own model, right? So how is it that you're able to? How is it that this is able to transfer from a model with your known weights to a model that where weights are unknown? How I guess intuitively does that kind of work?
So you're talking about how does the noise generalize to other models?
Yeah.
So this is something we tested. Originally, we trained very simple 2-layer CNN and generated the demarc noise for this, and it was able to affect a ResNet as well. So adversarial noise in general generalizes relatively well to other architectures, and we found that the simpler the original model, usually the larger, more advanced models would also be affected. Yeah.
Okay. Thanks. Sorry. My second question is, so can you somehow translate this gap in the classification accuracy to a confidence or some sort of how this gap is 90%. This is our data was used or something like that.
Yeah. That is definitely a topic for future work. Right now, it's a very simple threshold we set. If it's above, given that these two data sets are visually identical in most cases, the argument for when we see that the performance is so different, the argument can only be that the noise is different, and therefore, what can I say? The adversarial noise is not present in regular images. So if you can perform well on adversarial data that you've never seen before, it's because you have seen it before.
Okay, thank you.
So I was just wondering, so this is on classification, yes?
Yes.
So how would this translate to more complex kind of scenarios where you do localization or segmentation, pixel-wise kind of outputs, optical flow or something like that, like more complex kind of predictions?
Yeah, that's a good question. It's right now we are only looking at the classification because it's an easy way to investigate the performance differences between two models. But I think if you can find a metric where you can, let's say it's segmentation, you can look at how well the model segments your images, and if it does so better on the Deepmark dataset than your private dataset, that seems unusual if it's adversarially marked. Yeah.
Do you get similar effects if you add random noise to your images before you upload them rather than adversarial? Like, is that enough to sort of finger mark it? Or?
No, it is not. And neither is like a regular watermark as well. You would perhaps see the reduced performance in the top, but the thing is that these images are the same. So if you just degrade the visual a little bit and then train on them, they would perform well on the cleaner versions of those images on the bottom. Yeah.
What? Okay. How would you actually attack your Deepmark?
Yeah. So there are some defenses against adversarial noise. So you can train on adversarial images more generally to try and generalize better to that. So all sorts of attempts at combating adversarial attacks generally might have a positive, or in my case, a negative impact on this performance. But yeah, so those defenses might still be good. Yeah.
Okay, I'd like to stop here. Let's thanks for speaker again. Best student paper award and also best paper collaboration award from CPPL 2012. So his talk is nothing less last forever, harnessing the signal for dynamic scene perception. So yeah, we can go.
All right, can you hear me? Yeah. Cool. Hi everyone, my name is Mark. I think it's kind of funny that my talk follows a talk that's called Deepmarking. So hopefully this will be deep too. So for those of you who don't know me, my main passion is to sort of do computer vision tasks, but using novel types of perception, using like weird sensors. Now, actually most computer vision algorithms today rely on something that I call persistent features, right? So these are features that are part of the object surface, okay? So for example, the task of face recognition, right, relies on the facial features of a person. And because these features are persistent, it means that it's possible to identify a person even if that person walks outside the scene, comes back later, okay? Now, in today's talk, I'm going to talk about a less explored domain, and that is doing computer vision tasks using ephemeral features, right? Which are features that persist on the object surface for only a short duration. And I'm going to focus on two such features, vibrations and heat, but there are also additional features like that, for example, fluorescence. We've seen a lot of works about fluorescence. And as a side note, these ephemeral features are kind of interesting to our community because they cannot easily be captured with conventional cameras, right? They need someone like us to try to work with such signals. Okay, so today I'm going to talk about vibrations and heat. And in the first part of my talk, I'm going to show you how measuring transient vibrations, such as the vibrations that a ping pong ball creates when it hits a table, can be used to localize the impact location of the object. And in the second part of my talk, I'll show you a novel vision system that can basically paint and track its own patterns on completely textureless objects. So let's start by talking about vibrations, right? And vibrations are actually everywhere. You know, they're created by human speech, human movement, cars, the operation of electrical devices, and even natural phenomena like wind and rain. Now, in general, object vibrations depend on two things, okay? On the object material properties and the external forces that are applied on the object. Now, for the special case where the applied force is an impulse, the resulting vibrations can be divided into these two regimes, transient and harmonic. Okay, so what happens is that the impulse creates this transient response, right? That's going to contain a lot of frequencies, but then after a while, right, after a short while, most of these frequencies are going to decay, and the object is going to vibrate at its resonant frequencies or natural frequencies. Now, this process of measuring these resonant frequencies and mode shapes on multiple surface points is called modal analysis and has been used a lot in prior works to say something about the object material properties. But a modal analysis actually sort of ignores these transient vibrations that happen right at the start, okay? Now, there are also prior works that measure vibrations from some continuous excitation, like heartbeats, speech, and musical instruments. Now, these type of works usually focus on a particular object point, and they don't really care about sort of the spatial temporal relationship between vibrations at different points. So in the work I'm going to talk about now, we're going to focus on this sparsely explored domain, and that is the transient vibrations that happen right after an impulse, okay? But we're going to look at a very specific type of geometry, and that is just a planar surface. Okay, so what happens when you do this, when you knock on a surface? Well, I've already told you, right, that if we just wait for a couple of milliseconds, the vibrations are going to depend on the object geometry, okay? But what we actually show in this paper, right, that there exists a brief time interval right after the knock where the surface vibrations can be described as this elastic wave propagating outwards. You know, think of ripples in a pond right after you throw a stone, okay? Now, we show that by modeling the wave's geometry during this time interval and capturing the surface vibrations at a sparse set of object points, we can recover the impact location. Now, you're probably looking at this and thinking, well, here's the impact location, right? It's clear. It's right in the center of this big, you know, like circle. But this nice visualization that I'm showing you here is actually very hard to get, okay? It involves a laser Doppler vibrometer that scans the same knock on the same surface for many, many times over, right? To accumulate all these signals to create this nice visualization that you're seeing on your left. So now let's see how we do it, okay? So first of all, we have to capture these vibrations, right? And the way we do it at multiple points at once is using our dual shutter camera that we described in our 2022 CVPR paper. Now, as a quick reminder, the dual shutter camera uses speckle-based vibrometry. So we've seen a lot of speckle today, right? It's basically we are shining a laser on the object. It creates this speckle interference, and we are leveraging the memory effect to measure these vibrations at every point. Now, the catch with this dual shutter camera is that it can capture these vibrations, these shifts at 60,000 hertz using just these slow 60 and 130 FPS cameras. So that's the computational imaging trick of that particular camera. Okay, now what do we get for every point, right? So for every point gives us the surface tilt angles, which we can relate to the gradients of the vertical surface displacement. So at every point, we have this 2D geometric information, okay? So now let's focus on a single point, right? What happens at a single point? Well, at first, the wave doesn't even reach the point, okay? So we get like a 0 gradient. But then, as the main wavefront passes through our point, right, the gradient direction, the surface gradient direction, is going to oscillate between pointing towards the impact location and away from the impact location, many times over. You know, imagine like a buoy at sea where there's like a cyclone is coming. And then what happens? Well, that wave hits the boundaries of the geometry, comes back, interferes, and basically the gradient is pointing nowhere in particular for us. So during this entire sort of vibration period, right, from start to finish, there's actually just a short time interval, which we call the stable time interval, where the vibrations give us some meaningful information, and that is they are pointing either consistently towards the impact source or away from it. So using this insight, we developed a back projection inspired algorithm to accumulate the signal from all the points and figure out where the impact was. And by the way, our model includes both isotropic materials, right, where this wave is nice and circular, like you're seeing here, but also anisotropic materials like wood, for example, where the speed of sound is not the same at different directions, and there we approximate this wave as an ellipse. So let's see this cool experiment. So here's a ping pong table, right? And we place our camera to look at this ping pong table from below, okay? Complete non-line of sight, right? It doesn't see the player, it doesn't see the ball, it doesn't see anything. It only looks at vibrations at a couple of points from below, and then using only the vibrations, we can localize where the ball hits the table during a game. Here's another experiment. This time, we're going to point the camera at the floor, right? And then at these 5 points. And then someone's going to walk on this floor somewhere. And again, using the vibrations, we can try to localize where the person is walking. Now, these results are a little bit noisy for several reasons. One is the baseline between our measurement points and where the person is walking. But also, this surface actually deviates from our assumptions. It's not a homogeneous surface. It's a bunch of planks like stacked together. And also the footprint, actually the foot stamp the guy is doing is not a nice localized impulse. It has this spatial spread. But nevertheless, if we just add more points of measurement, we can significantly improve the localization. But by the way, this is a synthesized result because back at the time, our camera could only measure 5 collinear points. OK, so the key takeaway from this first part is that, you know, even though we were measuring these low-level signals, right, these vibration signals at particular points, we could actually sort of extract some higher-level, even semantic information about the scene. And sort of the interesting question for me is how far can we push this, right? Can we, for example, you know, sense the vibrations on the outside wall of some apartment and start to reason about what's going on in this apartment, right? Is there a person there? Where is that person? And maybe even who is that person, you know, depending on the vibration that they create. OK, so now we're going to switch gears and get to the next part, which focuses on a very fundamental task in computer vision. And that is this ability to recognize the same pattern from different views. Now, this simple ability, right, is critical for dynamic vision tasks, like structure for motion and object tracking, all right? But as we already seen in one of yesterday's talk, right, there's just a lot of parts of our environment where we simply don't have enough distinct features to complete this task, right? You know, think of this wall, for example. Okay? Now, in computer vision, we actually have 2 ways of handling this particular problem. Okay? And the first way is to just physically add these patterns to the environment, right? And this is very helpful. Like if you're like going to a robotics laboratory, you'll see a lot of these QR codes, plastered everywhere. They're easy to localize, easy to see, easy to track, but not very easy to sort of generalize into every surface that doesn't have any features. Okay, we cannot put QR codes everywhere. Now, there's a second way to solve this problem, and that is to project texture. Okay, and this works great for reconstructing static objects, but it doesn't really help us with dynamic tasks, right? Because the texture does not persist on the object surface. Okay, it's not like a physical texture. All right, but what if we could combine the advantages of both of these solutions? All right, what if we could project the texture, all right, remotely, programmably, but then also somehow magically make that texture stick on the wall, right? So we can basically use it as reference as our camera is moving. And of course, I mean, you see where this is going, right? We can use the second ephemeral feature that I was talking about, and that is heat. Let's paint these patterns with heat. So how are we going to do it? Of course, with a laser, okay? And how are we going to see these patterns? With a thermal camera. So here's the system we are proposing. It's a thermal camera combined with a laser that can walk around the scene and paint its own patterns on object surfaces. Of course, you can't see them in visible light, so you have to switch to the infrared domain. And there, you can see these patterns, you can track them, and you can use them for these dynamic vision tasks that I mentioned on completely textureless objects. Okay, so let's see an example. So here's this very dark mannequin head that I found on Amazon. We put it on a rotating stage, let it rotate. Now, if you take these frames, you plug them into a structure for motion engine, you're obviously going to get nothing, right? So here's me turning on my system, painting some points on the object, and this is what it looks like in the thermal domain, right? So every point I project is going to stick on the object. So now I can track these patterns, take these tracks, manually feed them into CallMap, and then get a really nice reconstruction of the camera motion, as well as the object geometry. So here's a schematic of our system, right? It's just a laser that we steer towards the scene using a dual-axis galvo. And we also have our LWIR thermal camera that is observing the scene in a coaxial configuration. Now, it's important to note that our system does not burn a hole on the wall in order to heat it up. In fact, the temperature rise that our system creates is very small. It's about, let's say, 1 degree or 2 degrees. It's far less than what you would get if you just put your hands on the surface and remove it, okay? All right, cool, so I showed you the system, right? I've shown you the patterns. I showed you that it works. Are we done? No. Why? Because remember the title of the talk, right? We're talking about ephemeral features. And our heat patterns are ephemeral, right? They diffuse and evaporate with time. So that means that if we take a picture of our nice pattern on the wall at time t, and then picture the same wall from a different vantage point, these patterns are not going to have a consistent appearance. And because these patterns will disappear in a few seconds entirely, we have to project these new points all the time. We have to reinforce the patterns with new points. And that is going to complicate the matching problem even more, okay? So what do we do? All right, one strategy is to say, okay, let's just take every vision algorithm and adapt it to this new type of data, right? Maybe retrain some networks. But we were lazy, We were like, okay, we want these 2 frames, these patterns, to act just like regular physical patterns. Why can't they just be consistent, like a QR code on the wall? And the way to achieve that is basically to train a neural network to learn to do how to do 2 things, right? The first thing it knows how to do, by the way, the input is always the second frame. So for every frame pair, we give it the later frame. And it learns to first remove those new points that didn't exist in the first frame, but then also to undiffuse the heat diffusion, to reverse the heat diffusion so that these patterns now match consistently. So let's see the effect of our diffusion correction network on another example. So here's another mannequin head, right? And if you kind of look at the points that I'm projecting here, you'll see that this time these points kind of diffuse rather quickly, right? If you try to track a single point, you'll see it disappears quickly. Now, if you just take frame pairs and plug them into an off-the-shelf tracker, you're going to get a pretty lousy result. But if you correct the frames before you plug them to that same off-the-shelf tracker, you can get a nice reconstruction of both the motion and the structure in this case. Okay, so let me show you some other easy applications that we can do with this, right? We can first of all do augmented reality without any markers, so on whatever surface we want. We're just going to project our own markers, track them, use them to superimpose something on the surface. We can do optical flow on completely textureless objects, right? Because we are projecting our own texture, then using it for whatever we want. And finally, we can do this fun indoor localization experiment. So here we put the system on a cart and direct it at the floor, right, using big mirror. And now I'm going to do like a loop around this office and hope I get back to the same point. And so this is how the process looks like. So you're seeing we're tracking the points we're creating on the floor. You know, think of a car driving on some dark road, right? And at the end of the day, you know, we get a nice closed loop. This is the camera motion in red. And by the way, this is kind of an impressive result because this is a completely open loop problem, right? There's no feature points that connect the first frame with the last frame. They're all long gone by now. All right. So before I conclude, I'm going to give you a teaser of actually another way that we can use heat as a visual cue. Okay? Now, in this second part, what I've shown you is that we can, basically use heat to paint these temporary patterns on object surfaces and then use them as reference. And also in this part, we treated the effect of heat diffusion as a bug, right? Something that we want to remove from our images to go back and so these images appear like regular physical texture. But if there's something that can be said about our community, I think, that if there's a bug, it could be turned into a feature, right? That's almost always the case. So in this case, the feature is that actually heat conduction, right, or the way heat diffuses on the object surface actually depends on the object geometry through this Laplacian in the heat transfer equation. So that means that by capturing a thermal video, right, of a static object this time, and observing the way heat diffuses or conducts on the object over time, we're able to invert the heat transfer function and basically get the shape of the object. Okay? Now, by the way, this is an upcoming work at ECCV led by Sriram Narayanan, who deserves all the credit for this thing and also all the questions. And the really cool thing about this method, right, is they can work for very problematic BRDFs, like transparent and translucent, right? All we need for them is to absorb some of the heat that we are shining on them, and then we can get their shape. Okay, so now I'm going to conclude, right? I think I've shown you that we can do some interesting computer vision tasks by sensing these non-standard features, right? We can sort of create on the object. They will last for a millisecond and then will disappear. And I think there's a lot more exciting opportunities for our community to do vision tasks with these novel signals, these weird signals that we get from all these emerging imaging technologies that you guys are using. And finally, a little bit of self-promotion. If you find any of these directions interesting, you too can be part of this research. Okay, I'm currently hiring students and postdocs and looking for exciting collaborations. So if you're interested, please shoot me an email or just talk to me today. Yeah, that's it. Thank you.
I think you said you wanted a question about the ECCV paper. So is there an active sensing component to this where the instantaneous estimation of the surface orientation can modulate where you point the laser to get more detail on the surface?
So for that second part, we're not using a laser. We're just using an uncalibrated light. No laser there. So think of a halogen bulb and another halogen bulb. That's it.
Okay.
Yeah, like a DC, large DC source.
Hi. Okay, I had a question. I had two questions, actually. So the first one is about the patterns that you project. So you're using visible light, right? Is there a way to make this subtle so that you don't see it or eye safe or something?
That's a great question. First of all, the reason we used visible light is that's because that was the laser that I had in the lab at that time. That no particular reason. Green is not great. You know, we're most sensitive to green. So if you're thinking about like the people around you, green is a terrible choice. You can maybe use infrared or even, you know, there's all these like eye-safe lasers where they have like a wavelength of over 1.4 micrometers, and they're supposedly stop at the the cornea, don't reach somewhere. I don't know, but one of the important thing about this method it doesn't come to replace for example, scanning someone's face, because people have like nice, good features. I mean, most people. It comes to supplement these parts where all of a sudden you don't have any features, then you can apply this thing. What was the second question?
Oh, yeah, so I haven't asked that one yet. The second one is about the ECCV paper, I guess.
Yeah.
How does it handle heterogeneous materials? Or can it?
So as far as heterogeneous materials, I think we don't have that modeled. I think, yeah, we just assume that the heat conduction across the material is a single parameter.
So yeah, this might be a dumb question, but I was wondering, like, what if you just use like an optical, like either a projector or like a DMD or a spatial light modulator, and focus that to the galvo and then project an optical pattern, and then you can use the same idea. You can use the galvo to move your projector around. Like, would that work in practice?
You mean to generate the heat?
No, then you're just completely operating on the optical scale. You're not doing any.
So you can scan a static object, right? If the object starts moving, you're having sort of problems where you have different geometric views. The point here is that we want everything to move freely. Okay, we want to paint a pattern that is your reference pattern on the wall. Okay. If you like remember the projector example, where you're sort of looking at a planar wall, right? It doesn't sort of matter how you project, you won't be able to figure out with good quality where you are.
Okay.
Okay, so this was also for the ECCV paper.
Okay.
So, I mean, I guess the diffusion should also change depending whether it's a solid object or a hollow object.
Right, right.
So how would you take that in account?
So what we do is we use an approximation of a surface. So we approximate that the object is approximately sort of like a surface, and we show in the paper that this approximation holds.
So it's basically a hollow object, and
yeah,
you
so
basically consider it to be
for the equation that describes the diffusion, it is like a hollow object, basically.
I mean, yeah, it's basically geodesics are the isocontours of
Yeah.
the diffusion, yes?
Yeah, hollow object, like you said.
Okay.
No more question? Oh.
So can you put your dots on snow or on metal?
Okay, metal, you can put the dots, but they will disappear basically almost immediately. So one of the limitations of this work is that you need to have a certain heat conduction for the material. So if you have a metal, you'll project a point, you'll see it, but then maybe 1 or 2 frames after, it will completely disappear. So maybe if you have a stronger laser, I don't know. I didn't check snow, so.
Okay, if no more question, we would like to conclude this session. So let's thanks the speaker again.
Well, before you can go to your well-deserved lunch, we have a few things still to do in our program. And the one thing, of course, that I'm sure everybody is looking forward to is the awards. So I'm going to turn it over to one of our website chairs, Yufan Ren, who has actually been running the technology behind the competition, and he will now give the award.
Okay, so hello everyone. My name is Yufan. Together with Dongqing Wang, we are the website chair. And thanks to your participation in this year's photograph competition, we have a very, very nice gallery of images that captures your best moment at the ICCP this year, and which will be available and will be available on the website of ICCP. And considering it is a competition, we have the votes, and I'm honored to announce our award for this year of the best photo competition, which is Quinton Q, and yeah, could you come forward to? Okay, so I'm just going to give this to you. And take it with me. Okay, so after me, I will turn it to Christina. Yep.
Hello, everyone. So I'm Christina, and along with Aditya and Eric, we are the poster chairs for this year. We received about 50 poster submissions and 5 demos. And then after that, we had an amazing jury who went around all the posters and made a short list of 7 posters that you all voted on this morning. And first, we're going to announce the best demo and then the best poster. So based on the audience vote, the best demo goes to Lensless PiCam, a hardware and software platform for lensless computational imaging with a Raspberry Pi.
for Eric Bezum, Stefan Peters, and Martin Viterli. So yeah, congratulations. So, thanks. And then I'm going to take a photo.
And so I'll announce the best poster award. So yeah, thanks to the jury who went through them and all of you who put in your votes. So for the best poster award, we have, go to the next one, Mid-Transient, Transient Light Transport in Mitsuba 3. So that's by Diego Royo, Miguel Crespo, Jorge Garcia, I guess, or Garcia Puello from Zaragoza University and EPFL. Congrats.
Thank you, everybody, for sticking out for so long. As you know, this year the program committee, the program chairs were myself, Wolfgang Heydrich, and Rohr Kostmeyer. And I wanted to thank you all for being part of the program first, and want to make sure that we thank all the folks who made the conference possible. And first and foremost, I want to thank the General Chair, Sabine Söstrank, who put in enormous effort behind the scenes, who put in enormous efforts behind the scenes to make sure that the program runs smoothly, tending to all aspects of the program, from organization, from making sure that we have a wonderful venue, making sure, I heard that she talked to the sun, the moon, to make sure we had wonderful weather, the clouds were at bay, there was no rain. We have to credit her for all that, and so thank you, Sabine. So credit where credit is due first. I have to first thank Sylvan for what I copied from his slide into the next slide. But in this particular instance, I thought it made perfect sense, and so I copied something from Sylvan's slide, as you can see. So for this entire conference, I think Raphael Lacto, who's right here, and please stand up. I think he was the Swiss Army knife that made sure everything was done. And so Raphael, thank you. If anything went right in this conference, Raphael made it go right. And so thank you, Raphael. Behind the scenes, we saw a lot of good papers today over the last 3 days. Behind the scenes, there was an army of program committee. This is our program committee for this year. They spent enormous amount of time, due diligence, to write really detailed, thoughtful reviews, and then spent time again to look through the author rebuttals, and during the discussion period, interacted with the other reviewers to understand the other reviewer perspectives, and tone down their own reviews and recalibrate as needed in order to come up with the decisions that we ended up with for the program. And so we have to thank all of these people for the quality of the program that we have today, that we have seen over the last 3 days. And so I want to flash this slide here. I'm not going to read out all these names, but I think the quality of the conference owes itself to these reviewers who spent due diligence, time, thinking in order to make the program a success. So let's give them all a round of applause. And of course, all these papers and posters that these people reviewed didn't write themselves. So I want to make sure that we thank everybody who was the authors and the creators of the excellent program that we had over the last 3 days. We had 3 wonderful keynotes, 8 invited talks, 12 proceedings papers that were presented, 6 PAMI special issue papers, more than 45 plus posters, 5 demos. All of this encompassed the program that we experienced over the last 3 days. And as you can all, hopefully you all agree that it was very good and high quality, and we have to make sure, let's take a moment to thank the authors, all the contributors in the various forms that made the program as high quality as it turned out to be. Just a couple of notes about the program itself. The entire, all the presentations, including the keynotes, the invited talks, the paper proceeding presentations, all of them have been recorded, and they will be uploaded to the YouTube channel in a few days, in a week or so. And so you will get to see them, and when you go back, you may want to, if there are papers that you want to share with your colleagues, then that's another easy way for you to share the program with the colleagues, with your colleagues as well. So, and then as Wolfgang already mentioned, the proceedings and the PAMI special issues will be in 2 separate proceedings. The ICCP papers will be in the ICCP proceedings, and then the special issue papers will appear as a special issue in IEEE transactions on pattern analysis and machine intelligence. And this year, as in previous years, we have a Best Paper Award. The program chairs selected a group of 6 papers that were forwarded to the Best Paper Awards Committee, and I'm going to call Ivo to announce the Best Paper Award.
Okay, thanks, Ashok. Yes, so we were actually asked at the start of the conference to deliberate basically which amongst these TPAMI papers would be receiving the Best Paper Award ICCP2024 this year. We attended every talk, we looked at every poster, we had discussions, we had internal discussions. Yes, it wasn't an easy choice, but ultimately we converged onto one particular paper which will receive the award. And I will read the statement by the committee. Yes. Okay. So, the Best Paper Awards Committee selected, how do I advance it? High-performance real-world optical computing trained by in situ gradient-based model-free optimization by Guangyuan Zhao, Zhou, and Renjie Zhou, all from Chinese University of Hong Kong. So here's the laudatio. Yes, this paper brings score-based training techniques from reinforcement learning into computational imaging. By allowing gradient descent without explicit forward models, their work provides a tool for overcoming challenges in hardware-in-the-loop training, a promising way to avoid the simulation-to-experiment gap commonly affecting CI systems. The committee recognizes the creativity and the importance of this work and believes it will inspire others to explore similar avenues. Congratulations to Guangyuan Zhao, Xinchu, and Renjie Zhou for this excellent work and the ICCP2024 Best Paper Award. There's a photo, I suppose, and there's a present too. So.
So in case you're wondering, the gift is actually a Swiss clock, right? And it's actually the one you see at all the train stations. This one happens, it might actually look familiar to you because Apple plagiarized a few years ago that watch. I think they have actually now, we treated that kind of watch, but so I thought it was a good gift to give everybody, because that army knife wouldn't go through airport security. And so we were thinking about something else, and guess whose idea it was? Raphael's, of course. So now it's my turn to actually say thank yous, and I'm going to make it relatively quick. But I do also, from my part, really want to thank all the speakers. I had a wonderful time. This was just absolutely a great program. Interesting, I learned new things, and I think you probably did too. Same thing to all the poster and demo presenters. It was very active. They tirelessly re-explained things to me if I didn't quite get it. So, and I think we had also a really great experience. To the program chairs, who put a wonderful program together. To the organizing committee, who really in the back, you know, there's also the finances to take care of, the website to take care of, the social media to take care of. So there's a lot of local organizing, but also remote organizing that goes in. To the volunteers, all the t-shirts, the blue t-shirts, and the photographer, and all the people who helped you out during this conference, thank you very much. And then, of course, to the sponsors who basically a little bit enabled that wonderful reception we had yesterday. And then, of course, last but not least, to you all for being an absolutely great, attentive audience. And I'll hope to see you again next year. So thank you very much. Now, it's not quite goodbye. You do get lunch if you want to. And it's actually sandwiches, so you could just pack a few and go and, you know, be at the lake if you want to and go out. But there is lunch provided. And so before you can actually leave, I want to turn it, you know, say goodbye to all of you, but turn it over to the organizers of next year's conference. And here is Kiras.
All right, so ICCP 2025, it's going to be in Toronto. It's going to be in this building that you see here. It is in basically downtown Toronto. It's on the campus of the University of Toronto. It's actually the building that you see here as well. It's just from the other side. It's the building of the School of Architecture. We're going to have a pretty nice venue for talks. So I hope to see you there. We are assembling our team. The program co-chairs, you see them here, Anat Levin, David Lindell, myself, and Renning. We will have some continuity in the organization of the finances as well as publications, and we are still assembling the rest of the team. So with that, I hope to see you all next year. And one last thing, we actually have a venue for ICCP 2026 as well. That is going to be in Princeton. So keep that in mind as well.